Welcome to the video lecture on integration of inverse trigonometric functions. In this video lecture, we're going to learn three new rules that you will want to have memorized for solving integral problems. These are going to be integrals involving inverse trigonometric functions. So here are the three that you need to know. If you see anything of the form the integral of du over the square root of a squared minus u squared, where u is a differentiable function of x, so that's where your variable will be, and a is some positive constant, then this integral is equal to the arc sine of u over a, or the inverse sine of u over a plus c. Notice that in this notation, when I say du on top, that means that whatever your u is a function of, the derivative of that function needs to be present in the top as well. Okay? Number two here, if you see anything of the form du over a constant squared plus a function of x squared, so a squared plus u squared, then that equals 1 over the constant a times the arctan of u over a plus c. And this is a very common integral problem that you will see, so this is definitely one that you want to have memorized. And then finally, the integral of du over the u times the square root of u squared minus a squared, and that is equal to 1 over a arcsecant of the absolute value of u over a plus c. So the major difference between 1 and 3 is obviously there's a u present in the denominator, and also the order is switched around. For arcsine, you just have the constant squared minus the function squared, and for arcsecant, it's the function squared minus the constant squared. So the x will come second for arcsine, the x will come first for arcsecant. And notice in terms of the formulas, the arcsecant formula does not have that constant 1 over a out front, but arctan and arcsecant both do. Okay? Now, these can be proven just by our differentiation rules, and it's only necessary to remember these three formulas since the alternative would just use negatives. For example, the integral of du over the square root of a squared minus u squared, that's arcsine of u over a plus c, but it's also the negative arccosine of u over a plus c. So you don't really need to know both, just memorize the arcsine. Okay, so let's practice using these. And again, one of the key things to remember is that when you use these formulas, whatever you let your u be, the derivative of that du, needs to be present on the top inside of that integral as well. So for a lot of these problems, we're going to be doing u substitutions to make sure that we're fitting the pattern the way we're supposed to. So if we take a look at this first example, we have the integral of 3 over the square root of 1 minus 4x squared dx. Now that 3 on top is not helping us whatsoever. It's not the derivative of anything at all. So let's just pull that 3 out of the way, and then let's kind of examine what we have here. Notice that the x squared term is coming second after the constant squared. So this makes it a candidate for this arcsecant. In order for it to fit this pattern, we need to identify what it is that's being squared for our constant, so what that a is, and what our u should be. So what squared gives us this 4x squared down here? Well, the a is easy because 1 squared is just going to be 1. So our a is 1, but our u has to be something squared so that once I square it, I end up with 4x squared. So this is a nice perfect square, and it's coming from a 2x. So if you were to square that, you would get 4x squared back. So the u that we want to use for our u substitution is going to be that 2x. Now, before we substitute in, let's find our du. So the derivative of u is just du, and the derivative of 2x is 2, and we put that dx on the side. So if you solve this for dx, we can divide that 2 over to the other side, which makes it become a 1/2 du is going to be what our dx turns into. So let's go ahead and substitute, keeping in mind that this square root in the bottom is really like a 1 minus 2x quantity squared under that radical. So this quantity squared is going to become our u. So we're going to have the square root of 1 minus u squared in the bottom. We'll have our 1 on top, our 3 out front, and then this dx turns into this 1/2 du. So now we've converted everything in terms of our u's. This 1/2 isn't doing me any good, so let's pull it out. 3 times a half is 3/2. So we have 1 over the square root of 1 minus u squared du, which is exactly this formula right here where the a is 1. So the integral of 1 over the square root of 1 minus u squared, that's just arc sine of u over a, which in this problem would be u over 1 or just u. And the 3/2 stays put. I'm going to resubstitute back in terms of x. So this u, remember, was 2x, so this becomes arc sine of 2x, and there's no bounds, so we're going to have a plus c. Okay? All right, let's try the next example. The integral of t over t to the 4th plus 16. So this is a fraction. We've seen problems similar to this in a previous lecture when we were talking about integrals of natural logarithms. So that is something that should kind of quickly run through your mind. Is it possible that this could be stuff prime over stuff? If you let your denominator be the stuff, the derivative of that wants to be a 4t cubed, and I don't have that in the numerator. I'm short several t's, right? I only have 1 t and I would need a t cubed. So this isn't going to be something that we could use a natural logarithm for. So an alternative, if you have something of this form, is to recognize that it sort of fits this pattern up here for our arctan. So what we want to recognize is what we have being added in the bottom here. Now the order is switched, but that's okay for addition. Addition is commutative, so the order doesn't matter. Subtraction, on the other hand, does matter, so that's why these are going to be two totally different answers over here for 1 and 3. So this is kind of like something squared plus something squared. Well, what is it that we're squaring? In order to get t to the 4th, we would have to start with a t squared and square that to get a t to the 4th. And in order to get 16, we would have to square 4. So this is going to be our u, and this is going to be our a. And that way we'll have our u squared plus our a squared. So the choice that we want to make for our u is going to be to let u be t squared. Now what does that require then for du? Well, the derivative of u is du, and the derivative of t squared becomes 2t dt. So that t on top is going to be really necessary because that's going to become part of this t dt right here. I don't have a 2, so let's divide that 2 to the other side and make it a 1/2 du. And that means this t dt right here is going to turn into a 1/2 du. And in the bottom, when I substitute in, remember that t squared squared becomes a u squared. And then we still have that 16 on the end, that constant of 16, which is really our 4 squared. So this integral turns into the integral of 1/2 over u squared plus 16 du. Now take that 1/2 and get it out of there. We don't need it inside of our integral. So this is 1 over u squared plus 16 du. So when you see these integrals that have a 1 on the top and a nice sum of squares on the bottom, that's going to be your clue that this is an arctangent. So this is an arctangent, but remember our constants. We need a 1 over a out front and arctangent of u over a. So this is going to be arctangent of u over a, and remember our a was this 4, the number before we squared to get that 16. So this has to be a 4. And whoops, sorry about that. And what we need out front is also a 1/4. So there's our 1 over a arctan of u over a. I also had this 1/2 from counterbalancing, so that is also still there. So this becomes 1/8 arctan of, now let's substitute in what our u was. Our u was t squared. So this becomes t squared over 4. There's no bounds, so we're going to put on our plus c. So for these inverse trigonometric function integrals, use a u substitution, especially if it's kind of complicated, to figure out what your u should be, what it is that once you square it gives you what you had inside of the integral to begin with. Figure out what your du is, substitute everything in, and then it should become more like those integral formulas that we just talked about. Let's try some more examples. Okay, the next one here, this one's a little bit of a tricky one. We have the integral of dx over the square root of e to the 2x minus 1. So it has a square root, which means this is either going to be an arcsine possibly or an arcsecant. And if you remember, the order here matters. If your variable is coming after the minus sign, where this u is, that's an arcsine. If your variable is coming before the minus sign, where this u squared is, then that's going to be an arcsecant. So if we look at this one, the x is coming before the minus sign. So this is, if it's going to be one of those three patterns we just learned, then this is probably going to be the arcsecant pattern. And that formula, I'll just write it up here so we can easily refer to it, should be du over u square root of u squared minus a squared, and that is equal to 1 over a arcsecant of the absolute value of u over a plus c. So what would our u need to be here? What function do you have to start with so that once you square it, you get an e to the 2x? Well, e to the 2x is really e to the x quantity squared, because you get to multiply powers when it's a power to a power, and x times 2 is 2x. So that means this is my u. So I need u to be just an e to the x. So then what would du need to be? Well, the derivative of e to the x is e to the x back again times my dx. So this is a tricky one, because in order for this to be an arcsecant, we do want that radical to start off with our u squared. And since e to the 2x is really an e to the x squared, or our u squared, then this does become u squared minus 1. But we have a little problem, because I don't have that u in the bottom. And in order to figure out what this dx is going to become, I need to solve for dx, which means we have to divide both sides by this e to the x. And that means dx would be du over e to the x. And we don't want to write it that way, because that mixes up your u's and your x's. We want this to be entirely in terms of just u's. Here's the thing to notice though, and it's easy to overlook. What is u? U is e to the x. So if I substitute this e to the x with a u, then that means du over u is what dx is equal to. So I'm going to replace this dx with du over u. So that one's a little bit tricky to see, and that's good news for us, because now I do have that u in the bottom that we need for this formula to work. So this is going to be an arcsecant where the a is just 1. So 1 over 1 out front here will just become 1. I don't even need to write that. And then I'll be left with arcsecant of absolute value of u over 1, or just absolute value of u. And now resubstituting back in terms of x, this becomes arcsecant of the absolute value of e to the x plus c. And you don't even need those absolute values, since e to the x is always a positive function anyway. So you can take them off if you want. Okay? There's our answer. So the trick to this one was to first recognize that u was e to the x, and then when we found our du and our dx, The dx required having an e to the x in this integral, which we didn't have. But since e to the x was our u, I could divide through by that e to the x, turn it into a u, and now my dx became du over u. And that made me have an integral only using u's, which is what I wanted. Okay? All right, let's try another one. The integral of 4x plus 3 over the square root of 1 minus x squared. So this time, the variable under that square root, we've got that difference of squares, so that's going to mean it's either an arcsine or an arcsecant, and this time the variable comes after the minus sign. So this is going to look sort of like our formula, potentially, of du over square root of a squared minus u squared, which is just arcsine of u over a plus c. So let's see if we need to utilize that at all here. First thing that I want to notice is that this numerator is kind of bad news for us, because in order to make this pattern work, we want our a to be 1 and our u to be x, and that means we wouldn't want anything in the numerator, and we've got extra stuff on top here that we don't want. Notice that that top is a sum of two terms. So what I'm going to do is I'm going to break this up into two different integrals. The 4x over that denominator plus the 3 over that denominator. The 4 and the 3 can both be pulled out because they're just constants. Now by breaking this up, now what we see are two different integrals. This one has an x on top, this one does not. Now the one that does not have an x on top is your arcsine, because there's no u on the top here. The derivative of our x is just 1, so we just want a 1 on top. So this right here is going to become arcsine of just x, because our a is 1, so x over 1 just becomes x. So that one is actually done. This one's a little bit trickier to see. What you might have to do is notice that that square root in the bottom is kind of like an outer function. If you need to, you can move it up to the top and make that power become a negative 1/2. And that x on top is actually going to help us, because if we do a little bit of pattern recognition, this is my outer function, this is my g, and the derivative of that 1 minus x squared wants to be a negative 2x. I need that x in there. What I'm missing is a negative 2. So if I put that in there, I'll have the right g prime, but I have to counterbalance by dividing by negative 2. So by having that extra x on top, that helped us have the derivative of this inside function. So we are able to change this into our pattern recognition and do it that way. When you don't have that x on top, then that's when it becomes that arcsine. Okay, so how do you do pattern recognition again? First, make sure that you have your f, your g, and your g prime, which we all do, and then you just integrate only the outer function. So the integral of something to the negative 1/2, we add 1 to that power, which makes it become a positive 1/2, multiply by the reciprocal out front, which would just be a 2, and then don't forget you have these constants out front. 4 divided by negative 2 is a negative 2, and it's going to multiply by what we have right here. What's inside stays inside. So what we have then is this becomes negative 4 square root of 1 minus x squared plus 3 arcsine x, and then there were no bounds, so we have a plus c. Okay, so big difference between these two integrals here and here. The one with the x enabled us to use pattern recognition because the derivative of what was inside of that radical needed that x. for this one, there was no x, so we wouldn't be able to do pattern recognition because we're missing some variables. So that's when we recognize that this is that inverse trig function arcsine. Okay, let's try a couple more. The next one here, we have the integral of 3 over 2 square root of x times 1 plus x dx. So first things first, I've got a couple constants here, 3 over a 2. I don't like those in there, they just complicate things. So let's pull them out right away. And then we're left with 1 over square root of x times 1 plus x dx. So here's what's running through my head when I look at this. I see a fraction. So I want to think first and foremost of, could this be stuff prime over stuff? No way, because the denominator is too complicated to have just a derivative of 1 on top. So that doesn't work. Now also, it's a fraction with a radical in it, so does it possibly fit one of our new inverse trig rules that we talked about? And the answer to that is no, because what's under that square root doesn't look like a difference of 2 squares. It's just a plain old x. So that doesn't work either. So what we're going to need to try if all of our other options fail is some kind of a u substitution. Now here it's kind of difficult to know what a good choice for our u should be. There's really probably only two choices. Either you let it be the square root of the x, or you let it be the 1 plus the x. Now how do you know which one it is? Basically by experience, by knowing how this is going to work out. If you make the wrong choice, you'll see that, because once you choose that u and plug everything in, you'll not make any progress towards getting an answer. So that's when you scrap it and you choose a different u instead. So I'm going to let my u be the more complicated of these two expressions, which to me is that square root. So I'm going to let u be the entire square root, not just what's inside, because letting u be x does nothing for you. That's just a change of variables. You want u to be a function of x, so let it include that square root. Now when we let u be a square root, there's a trick here before you figure out what your du is. Remember that if you have a square root involved, it's easier to square both sides first. So this would become u squared equals to x. Then take the derivative of both sides. The derivative of u squared is 2u du, and the derivative of x just becomes 1 dx. So we're ready to start plugging some things in. That 3/2 stays out front. We have a 1 on the top. This square root was our u. This we need to figure out. So how do I figure out what 1 plus x is? Well, I need to know what x is in terms of u. And I know that. I know that x is u squared. So this denominator actually becomes 1 plus x, and x was u squared. And then this dx becomes 2u du. Okay? So now when we go to simplify, the first thing that I notice is that I have this u on the top and this u on the bottom, so those actually cancel each other out. And I have this constant 2, which I don't want, so I'm going to pull it out, and that's actually going to cancel the 2 that was in the bottom of my fraction. So now I'll only have a 3 out front. So this is gone, so all that's left inside of my integral is 1 over 1 plus u squared du. So when you see something like this, there's usually a couple options here. You see that sum of 2 squares on the bottom. So this is either going to be an arctan if that numerator is a 1, or it could be, possibly an ln if you had a u on top to be the derivative of this bottom. So it would be a stuff prime over a stuff. We don't have a u on the top, so this is going to be arctan, where my a is 1. So that 3 will stay put. I would want 1 over a, which is just going to be a 1, times arctan of u over a, or just u, and then we have to resubstitute back in terms of x. The u becomes our square root of x. There's no bounds, so then we have our plus c. Okay? All right. Next one here. the integral from 0 to pi over 2 of cosine x over 1 plus sine squared x dx. So, couple things to think about. When you see fractions, I always recommend looking for stuff prime over stuff first, and then if that doesn't work, then consider other possibilities like these inverse trig functions or pattern recognition or some kind of u substitution. So when I look at this, the denominator would be 1 plus sine squared x, and the derivative of that would require a chain rule on sine squared x. You'd have to bring down the 2, subtract 1 from the power, so you'd get 2 sine x to the first, times the derivative of what's inside, which would be a cosine x. That is much more complicated than what I have in the top. So this is not going to be a natural logarithm, at least not initially. So if that is ruled out, then the next thing to consider is, can I rewrite this in some way? And what could I do to manipulate it to make it into something I do know how to integrate? Well, this is kind of like a sum of squares in the bottom, right? It's 1 plus sine squared x. And we just talked about that over there. When you see a sum of squares, then usually that's either going to be some kind of an ln if your numerator is the derivative, which this one we already said was not, or it could potentially be an arctan. And in order for this to be an arctan, we want to use our u substitution to put it in the right form. So what should our u be? Well, it's going to be whatever this function of x is before you square it so that you get sine squared x. So that means our u has to just be a sine of x, so that this would become 1 plus sine of x squared, or 1 plus u squared on the bottom. So if that's my u, then what would du be? Du is the derivative of sine x, which is cosine x dx, and that is exactly this. So this is going to become a du. So that means we have cosine x dx becomes our du, and in the bottom we have 1 plus u squared, and there's nothing left in the top, so this is going to be a factor of 1. We already used that cosine. It got absorbed into this du. So this integral just turned into 1 over 1 plus u squared, which is perfect because that's our arctan, where the a is 1. So this is going to be 1 over a, or 1 over 1, arctan of u over a, or just u over 1, which is u. We do have some bounds here, so I'm going to go ahead and substitute back in terms of x. U, remember here, was sine of x. And now I'm going to use my x bounds, so 0 and pi over 2. So this is going to be arctan of sine of pi over 2 minus arctan of sine of 0. And we should know those values. Those are good values. Sine of pi over 2 is 1. Sine of 0 is 0. So this is arctangent of 1 minus arctangent of 0. Now these are values you should know as well. If you need to, remember arctan is the same as inverse tangent. So this could be written as inverse tangent of 1 minus inverse tangent of 0. If you prefer that notation, that's okay too. So to figure out what these are, remember that an arctan or an inverse tangent is actually finding us an angle. So the tangent of what angle gives us 1? So when you take the tangent of what angle do you get 1? Well, that's pi over 4, because tangent is sine over cosine. So sine of pi over 4 over cosine of pi over 4, those are both root 2 over 2, so that goes to 1. Okay, now let's try arctan of 0, or inverse tangent of 0. So tangent of what angle gives us 0? Well, that's just going to be 0, because sine of 0 over cosine of 0 is 0 over 1, or just 0. So the tangent of 0 is also 0. So pi over 4 minus 0 is pi over 4. Okay? Okay, The next couple of examples are going to use a new technique that we haven't talked about yet. When I look at this integral here, I see a fraction. Unfortunately, the denominator, if I let that be my stuff, the derivative of that wants to be 2x plus 2. And on top I have 2x minus 5. So it's not quite stuff prime over stuff, so it's not quite going to be an ln, at least not yet, without some work going on. It also is a rational function, and sometimes, like we talked about in a previous lecture, if you look at the degrees of the top and the bottom, sometimes you can use long division to help you out. Unfortunately, we can't here because the degree on top is 1 and the degree on the bottom is 2, so the top is smaller than the bottom, so we can't use long division. The third thing that's wrong with this is if we think about using some of these inverse tangent or inverse trigonometric functions that we talked about, you would need to see something squared plus something squared, or you would need to see some square roots, and we don't have any square roots at all involved here. So if this is going to fit our inverse tangent, it would need to look like a du over u squared plus a squared, or a squared plus u squared. The order doesn't matter. And then that would be our arctangent. So we would need to make this look like u squared, so some function of x squared plus a squared. And this denominator does not look like that because we have this middle term. So what we're going to do is we're going to turn this denominator into a quantity squared plus a constant squared. And to do that requires that we factor this denominator in a special way using the process called completing the square. And most of the time we don't like doing this because completing the square can be a little bit tricky. Okay, so here's what we're going to do. We're going to take just that denominator. We're going to work with this denominator for a moment. And when we complete the square, I'm going to leave a little bit of space here, and I'm going to push that plus 2 off to the side. We're going to ignore that plus 2 initially. What I want to focus on are the x terms and how I could get that to factor. Well, I want it to factor into some quantity squared. And in order for that to work, I would obviously need an x plus something. And the term that would need to go here should be half of this middle term, half of 2, which is 1. The reason why I need that is because if I were to FOIL this out, I would get an x squared, I would get an x plus an x, which is this 2x, but I would also get a plus 1 on the side, which this original problem didn't have. So what we're going to do when we complete the square is we're going to add in that 1, but at the same time we're going to subtract it off. So we're adding in a fancy version of 0. So we're not changing the problem at all, we're just rewriting it in a different way. So then these three terms become this quantity squared, and the minus 1 and the plus 2 give me a new constant on the side. So this denominator is now going to be written as x plus 1 quantity squared plus 1 dx. And the reason I did that whole process is because now this quantity can be my u, and I can make this denominator look like a u squared plus 1. So it's going to have this form that we need to do an arctangent. Okay, so that's kind of our plan. So let's let u be that x plus 1. So then what would du need to be? Well, the derivative of x plus 1 is just 1, and we put that dx on the side. So the denominator becomes u squared plus 1. The dx is just a du, but now we need to figure out what this top is going to become. And in order to figure that out, I need to know what x is in terms of u. So go to here and solve this for x. X is going to be u minus 1. So let's substitute that in right here. So this will be 2 times parentheses u minus 1 minus that 5. And let's clean it up. We're going to get 2u minus 2 minus 5 which becomes 2u minus 7 over u squared plus 1 du. Now, in that numerator, I don't want anything to show up there if this is going to be an arctangent. I want a 1 on top. So what I'm going to do is I'm going to split this numerator up into two different integrals. The first one will be just the 2u over the u squared plus 1. And then the second one, I'm going to subtract here, will be that 7 over the u squared plus 1. So if I pull that 7 out, then for this second integral, I do have now that 1 on top, so this one will become that arctangent. So this is going to be minus 7 arctangent of just u, since my a is 1. Now what about this integral here? Well, this one is not going to have a 1 on top because it's got that variable. And if you have a variable on top when you have that sum of squares, then that's typically going to be an ln, because you can probably make this become stuff prime over stuff. And in fact, this one already is, right? If this is your stuff, the derivative of that is 2u, which is exactly what I have on top already. So I don't even need to fix anything. This is going to become the ln of the absolute value of this stuff in the bottom. So u squared plus 1 in absolute value. And there's no bounds on this, so I'm going to put in a plus c, but I'm not quite done yet because this is still in terms of u. So what I need to do to finish it is go back up here and remember what u was equal to. It was x plus 1. So we're going to substitute in an x plus 1 right here and an x plus 1 in parentheses right here. Now you can stop here. That's the correct answer. If you wanted, you could expand this all out, and guess what you're going to get if you expand out x plus 1 squared plus a 1? Well, that's exactly this. So if you undo all this work, you're going to get back x squared plus 2x plus 2. So you could also write this as x squared plus 2x plus 2 inside of that ln. That's just an option. Okay, so here's an alternative answer. So completing the square, you would use that when your denominator here does not have that nice factored form so that it looks like a sum of two squares. If you get this middle term in here that's kind of messing things up, then that's kind of the clue that you want to complete the square. All right, let's try another one like this. So this integral is the integral of x over the square root of 9 plus 8x squared minus x to the 4th dx. So this time we do have that square root in there. So if this is going to be an inverse trigonometric function, then it's going to either need to be an arcsine or an arcsecant. So the arcsine was square root of a squared minus u squared. And then the arcsecant had a u out front, square root of u squared minus a squared, and that was 1 over a arcsecant of absolute value of u over a plus c. So looking at these two formulas here and trying to figure out which one it's going to be, I notice first of all that there's no variable out front of my square root in that denominator. So most likely it's not going to be this arcsecant, but you know, there's still potential for that depending on how we choose our u. Okay? The other thing to notice is that we do have this x on top that neither of these two formulas have. So hopefully that x on top is going to become a part of this du. So what we need to do is figure out what this denominator is going to become. And if we're going to make it fit one of these two formulas, then we need to make this look like a difference of two squares, a constant squared minus a function of x squared, or vice versa. So let's focus on this denominator, and let's see if we can complete the square to turn it into a difference of two squares. So just focus on the stuff underneath the radical. Now, there's a little bit of an issue here, and this may just be my personal preference, but I like, when I complete the square, I like to put these terms in descending order. And the fact that this leading term, this x to the fourth, is negative kind of makes your life more difficult. So what I would recommend is factoring out that negative from all three terms here, and then completing the square on what's inside. Okay, so you can either work on that over to the side over here or work on it within inside of these brackets. It's kind of up to you. So if we work inside of our brackets, just make sure that you leave that negative way out front. Now I don't want to deal with this minus 9, so I'm going to push it off to the side, and I'm going to leave some space for that sort of missing number that I'm going to need to add and subtract when we do this completing the square process. Now what I want to do is factor these two terms into some quantity squared. Since this is an x to the fourth, I'm going to need to start with an x squared inside of here. And if I take half of this middle coefficient, then that means I need to have a minus 4. So that if I were to square this out, I'm going to get an x squared squared, which is x to the fourth. I'm going to get a minus 4x squared and another minus 4x squared, which is the minus 8x squared. And then on the end, I'm going to get a plus 16, because negative 4 squared is 16. So I need a plus 16 in order for these three terms to factor into this correctly. So I have to counterbalance with a minus 16. So that makes these two numbers combine into a negative 25. Now if we redistribute our negative across, I'm just going to put the minus in front of my parentheses like this, and then I'm going to change the sign of my 25, and just to make it look cleaner, let's put the 25 first minus the x squared minus the 4 quantity squared. So this denominator is now the square root of 25 minus the quantity x squared minus 4 quantity squared dx. So this is now a difference of two squares. This is going to be my a squared, this is going to be my u squared. So what should my u be? My u needs to be what's inside of these parentheses. So we're going to need to let u be x squared minus 25. And that means our du is going to be the derivative of that, and the derivative of x squared is 2x, the 25 goes to 0, and then we have our dx. So this x on top does become part of my du. I don't have a 2 in there, so let's divide by 2, and then we can change this x dx into a 1/2 du. The square root on the bottom becomes a 25 minus our u squared, and I used up this x already as part of my du, so there's nothing left on the top but a factor of 1. So with a lot of work with completing the square and a little u substitution, we were able to turn this really messy integral into this one right here. So now let's take this 1/2 and pull it all the way out to get it out of there, because it's not helping me at all. And now this does fit the pattern of our arc sine. The u is coming second after the minus sign. The a is a 5. Okay, so that means this integral, I'm going to leave the 1/2 where it is, this integral becomes the arc sine of u over a, so u over 5. And if I resubstitute back in terms of x, that u becomes x squared minus 25. Sorry, that was a typo on my part up here. Shouldn't have been a 25. It should have been the 4. Sorry about that. Doesn't affect any of our work here. I just wrote it wrong initially. So this was my u. So this should have been x squared minus 4. So when I resubstitute back in terms of x, this becomes x squared minus 4 over that 5 and the 1/2 stays out front. There were no bounds, so this is a plus c. Okay? So our u was this quantity right here, and our a was the square root of that 25, which was our 5. Okay? All right, so completing the square. Look for that when you have a trinomial in your denominator that doesn't seem to factor nicely. Try completing the square on it to turn it into either a sum or difference of a quantity squared plus a constant squared or minus a constant squared. Okay, next example. The integral of the square root of x minus 2 all over x plus 1 dx. So here's what we have. It's a fraction. We obviously do not have stuff prime over stuff, so that's not going to be an ln, at least not initially. And it doesn't appear to have anything like a sum of squares in the bottom or a difference of squares under a radical in the bottom. So it doesn't look like it's going to be an inverse trig function either. So what do we do if we're not quite sure what to do? We try a u substitution. So we're going to choose our u here. Now you could let u be your denominator or your numerator. It's kind of up to you. Out of the two things, out of those two choices, I would probably choose my u to be the more complicated expression, namely the one with the square root. Okay? So I'm going to let u be the entire square root of x minus 2. I tend to find that letting u be the entire square root makes my integral get simpler. So I use the square root in my u substitution. Now don't forget that when you do that, you want to square both sides first before you take your derivative. So the derivative of u squared becomes 2u du, and the derivative of x minus 2 is just a 1, so that's going to be just a dx. Now in this integral I see some x's, okay? This one right here, that's just our u. And this dx is now going to become a 2u du. But I do need to know what x is by itself so I can add 1 to it. So that's where we're going to go back to here. And if I add 2 to the left side, then that tells me that x by itself is u squared plus 2. So I am going to put in u squared plus 2 for that x, and then I have to add 1 to that. So there's my x plus 1. Now this 2 I'm going to pull out, and then on the top I have this u times this u gives me a u squared, and on the bottom we have a u squared plus 3. So look at the integral that we now have. This is a nice fraction. We have kind of a sum of squares in the bottom, even though 3 is not a nice perfect square. This really is a sum of two squares, so that makes it eligible to be possibly an inverse tangent. However, we have a u squared on top. Now that makes this a rational function, and if you look at those 2 degrees, they're equal, which means long division is probably a good option here. So your long division would take that u squared on the top, and then you would divide by the u squared plus 3 in the bottom. U squared times 1 is u squared, 3 times 1 is 3, but we have to subtract these, so I change my signs. These cancel out, and that means my remainder is negative 3. So u squared over u squared plus 3 becomes 1, this big 1 right here, minus my remainder 3 over u squared plus 3. So the integral of this is going to be the integral of each of these. Okay, now that's perfectly fine. I want to show you something here as an alternative to long division. It doesn't always work, but in this problem it actually works pretty slick, and it's a nice quick option for you. The option here is to add and subtract in a constant into that numerator to make this reduce nicely. So here's what I'm going to do. Let me move this du off to the side just a tad so we have a little bit of space. Notice that that denominator is u squared plus 3, and my numerator is almost identical. It's just the u squared. So if I had a plus 3, then these would cancel nicely to just a 1. But I can't just add in a 3, so I'm going to counterbalance by subtracting 3 as well. So I've added in a fancy 0. However, these terms do reduce to a 1. This fraction here gives me minus 3 over u squared plus 1. Oops, sorry, u squared plus 3. So by adding and subtracting that 3, I was able to reduce these 4 terms into a factor of 1, and then that extra little minus 3 over the original denominator is kind of like my remainder. And notice that is exactly what we got right here. So this little trick of adding and subtracting gives you the same exact result as long division. It's just a little bit quicker sometimes. Okay? So let's go ahead and proceed from here. We still have this 2 out front, and now we're going to integrate these 2 terms instead. So let's break it up into 2 different integrals. I'm going to leave that 2 way out front with brackets, and I'm going to break this up into the integral of 1 du minus the integral of 3 over u squared plus 3 du. Now the integral of 1 is good, right? What function has 1 as its derivative? Well, that would just be u. Minus this one is good but not great. We need to pull this 3 out, and that's going to give me a 1 on top. And now it is something we can handle, because with that 1 on top, this has the look of an arctangent. Unfortunately, we don't have a nice perfect square where this 3 is, but that's okay. What number, when you square it, gives you 3? The square root of 3. So our a is going to be square root of 3. So let's write out what this becomes. This 3 stays put, and then this is an arctangent. It's going to be 1 over a, and our a is root 3. Arctan of u over a, so u over root 3, and there's my integral. Let's go ahead and distribute our 2 across. So this becomes 2u minus 6 over square root of 3 arctan of u over root 3. And we can resubstitute back in terms of x. Here is what u was in terms of x. So this becomes 2 square root of x minus 2 minus 6 over root 3 arctan of square root of x minus 2 over root 3, and then there were no bounds, so this is a plus c. I don't mind having radicals in the bottom, but if you didn't like that, or if you were checking your answer in the back of your textbook, it would probably rationalize the denominator by multiplying by root 3's. So this would become 6 root 3 over 3, which is 2 root 3. So this would be minus 2 root 3 arctan. And then if we have square root of x minus 2 over root 3, and I rationalize that denominator, then this would be the square root of, if you distribute that 3 across, this could be 3x minus 6 over 3. This is just an option. Okay, usually I don't bother doing that unless I really need to make it look nice. Okay? Alright, next example. Find the area under the curve y equals e to the x over 1 plus e to the 2x for x in the interval 0 to ln of root 3. So these are the endpoints for the x values under this curve. So you can draw this on your calculator, type this into your y equals, look at your bounds by setting your window to be from 0 to ln of root 3 for your x min and your x max. And you're basically just finding the area under that curve. Well, what is that called when you find the area under a curve? That's called a definite integral. So this problem is really just asking for the definite integral, which has bounds from 0 to ln of root 3 of this curve. So that's what this problem is really asking for. This is the area under that curve. So if we can evaluate this definite integral, we'll know what that area is going to be. So look at this problem. What could this possibly represent here? Well, in the bottom we have 1 plus e to the 2x, and that e to the 2x, we did a problem earlier today like this. This is like an e to the x squared. So this is like a sum of two squares in the bottom. So potentially this could be an arctangent. In order for it to be an arctangent, our u would have to be that e to the x, which means our du would have to be e to the x dx, which is exactly what my numerator is. So this is perfect. Let's do a little substitution. This e to the x dx on top becomes my du, and on the bottom, this 1 plus e to the x quantity squared becomes 1 plus u squared. And that is exactly an arctan where the a is 1. So this is going to be 1 over a, or 1 over 1, arctan of u over a, or u over 1, which is just u. Now we did have some bounds here, but they were x bounds. So I'm going to go ahead and resubstitute back in terms of x. X, or u, was e to the x. So let's put in our e to the x. And then I can use these two bounds. So we're going to substitute in arctan of e to the ln of root 3 minus arctan of e to the 0. Now e to the ln of root 3. Ln is base e. If these two bases match, e raised to an ln, those cancel out because exponents and logarithms are inverses of each other. So this is just root 3. So all of this becomes root 3. And we still need to do the arctan of that. E to the 0 is just 1. Now if you need to, you can think in terms of inverse tangents and write it this way. Okay, that's kind of up to you. But remember that an arctan or an inverse tan is actually finding us an angle, something in pi. So what angle, when you take the tangent of it, gives you square root of 3? And this comes from that unit circle. And the answer to that is pi over 3. So the answer is pi over 3 because tangent of pi over 3 would be sine of pi over 3 over cosine of pi over 3. And pi over 3 angles, the sine value is root 3 over 2 and the cosine value is 1/2. And these halves cancel, so this is just square root of 3. So that's why pi over 3 is the answer. Similarly, inverse tangent of 1, we did this one earlier, that answers pi over 4 because sine of pi over 4 is root 2 over 2, cosine of pi over 4 is root 2 over 2, so that cancels out to 1. So then if we get a common denominator of 12, this becomes 4 pi minus 3 pi, so our final answer, our final area, is pi over 12. Okay? All right, last page here is to look at some integrals here and determine which of the following integrals can be found using the basic integration formulas that we have learned so far. So which ones of these are either directly a formula we know or could be manipulated to become a formula we know, and which ones can't we do at all. So if we look at this first one, the integral of dx over x square root of x squared minus 1, this has that difference of squares under the square root with the x coming first, and we also have the x on the outside. So that is exactly our arcsecant. And this is going to be the a being 1, so this would be 1 over 1 arcsecant of x over 1. So just arcsecant of x in absolute value plus c. So that one we definitely know. How about this one? The integral of x dx over the square root of x squared minus 1. This time the x is in the top instead of the bottom. So it's not one of our direct integration formulas that we could just look at and spout out the answer, but this is one we can manipulate into something we do know how to integrate, because that x on top is actually going to become part of the derivative of this inner function. So we're going to do a little pattern recognition here. I'm going to move this x squared minus 1 up to the top and make it negative 1/2 power. And then we have this x dx still. then my outer function is the negative 1/2. My inner function is this x squared minus 1, and the derivative of that is a 2x. That's what that x is for, because if we put a 2 in front of it, now we have the right g prime. I counterbalance by a 1/2, and I integrate only my outer function. So the integral of a negative 1/2, when I add 1 to that, becomes positive 1/2 times 2, and what's inside stays inside. These cancel. So this is just the square root of x squared minus 1 plus a c. So having that x in the top became a part of that g prime, or that du, if you will, if you wanted to do a u substitution here. Okay? So then this third integral here doesn't have the x at all. It's not in the bottom, so it can't be an arcsecant. It's not in the top. And you can see that this pattern recognition, or this u substitution, wouldn't work unless you had that x. Because if you let your u be this quantity inside that square root, the derivative of that has to have an x, because it would be 2x. And I need that x in order to get the correct du. So this is one that we wouldn't be able to do because it's missing that x. Okay? So now let's look at some with some ln's in it. And these can be tricky, all right? Here we have the integral of dx over x ln x. So is this something that we could do? Well, it doesn't fit any of our strategies of the inverse trig functions, because it doesn't have any square roots or sum of squares or difference of squares. So none of these last three are going to be inverse trig functions at all. But do they fit any other possible problems that we've done in the past? Well, this one could be done with a u substitution. We've done this problem actually in a previous lecture, or something very similar to it, where we choose the u to be something in here that also has the derivative present as well. And the best thing to choose for your u here would be to let it be that ln of x, because the du would then be the derivative of ln of x, which is 1 over x dx. And that could be thought of as a dx over an x, right? If you just rewrote it in a slightly different way. And that's what this is right here. So this dx over x becomes our du. And the ln of x on the bottom becomes a u in the bottom. And this is exactly an ln. This is stuff prime over stuff. The derivative of u is 1. So this has as its antiderivative the ln of the absolute value of u. If we substitute back in terms of x, u was an ln. So this is the ln of the absolute value of the ln of x. And there's no bounds, so it's a plus c. So we chose our u to be ln of x because the derivative of that is 1 over x, and that is exactly what I had. I had that extra x in the bottom, which becomes a part of that du. Okay? So this next one's very similar. The only difference is the ln of x is now on the top. But we're going to do it exactly the same way, because if you let your u be ln of x, then your du becomes 1 over x dx, or dx over x if you push it together, and that's what this is. So again, that extra x in the bottom is what's making this work, because that dx over x becomes our du. This time the ln of x was in the top, so my u goes in the top. So this isn't going to have an ln of u as its integral. It's actually now a power rule, because this is like u to the first. So this becomes u squared over 2, which when I replace it with an ln of x, becomes ln of x squared over 2 plus c. So same substitution, but when the u ended up being in the bottom, that gave me an ln. When the u ended up being in the top, that gave me a power rule. So then how about this last one? How could we make this work? Well, we can't, because if we let our u be ln of x, that requires that the du have a 1 over x dx, and there's no extra x in the denominator here to absorb into that du. So this one would be impossible because we don't have the correct du. Okay? Alright, you just added 3 more new formulas to your list of integration rules. So memorize them. They do pop up quite a bit, and it takes a lot of practice to get the hang of them. So hang in there. Alright, that concludes our video lecture on integration of inverse trigonometric functions.